Well, hello YouTube. I'm back with part 4 of my video series on how to calculate the curvature over the Earth's surface. This one we're talking about obstruction height, which is what you would expect not to be able to see in the bottoms of the buildings in a distant skyline. So we had to add a little bit of height here, both from an observer's point of view and from the skyline that we're viewing. So this is us standing above the surface of the Earth because nobody ever lays down on the surface of the Earth and views a distant skyline. You have some height anyway. And so what we're going to add in here and what we're going to be calculating this time is we got to add in our line of sight. So there's our line of sight, and this little piece here is what we're going to be calculating because that is the amount of the distant skyline that has been obstructed because of this curvature of the Earth. We can't see through this bulge, so it is blocking our view of the bottoms of buildings, of ships, etc., in the distance. So I'm going to have to use this as more than a mile this time. We're going to have to use that. I think I'm going to use 6 miles. You don't have to be very high above the surface of the Earth before you can see further than a mile. So I'm going to use 6 miles from point to point. And the reason I'm going to use 6 miles is because that is what a lot of people talk about. That's the distance of the Bedford level experiment. So we're going to use the 6 miles. Now, down in here is the first thing we're going to calculate. We're going to calculate that angle, and we're going to call it theta, and you will notice that that is actually the first thing we've calculated in every single type of curvature that I've talked about. So I've got this a little bit more organized because it's a little bit more complicated to do this. There's more steps involved. So I've got the steps laid out here in a little bit of wording. So finding theta, we need to know the distance to the target, which I've just said is 6 miles along this curve. That 6 miles is not this straight line distance, but along the surface of the Earth. And we'll use 6 miles for this example. So we're going to find that theta. And notice right now, to find this theta, I don't need to know how high this is, but we're going to take that into consideration later. So we're going to have theta when compared to the entire circle, which is 360 degrees, will be the same as when I compare this arc here to the entire circle. So that arc is 6 miles, and the entire circle will have a circumference of 2 pi times 3959, which is the radius of the Earth in miles. Now, in order to solve for this angle, I need to multiply both sides by 360 degrees. Theta is being divided by 360 degrees, so to get rid of it, we do the opposite. So I'm going to multiply both sides by 360, which on this side gives me 6 times 360, divided by 2 pi times 3959. Now I'm going to pull up my calculator and actually calculate that. I got a better calculator now than I had before. And let's actually plug this in. 6 times 360 divided by 2 times pi times 3959. And let's see what we get. Okay, 0.0868. So let's take that number, we'll put it down here, and maybe make it a little bit smaller. So there is our angle theta. Now, that's in degrees, so we're going to go on to step 2. And step 2 requires that now I draw in this line. Now, why I'm drawing in that line, this line is going from the center of the Earth to the point of tangency of our line of sight on the Earth. Now, this is one of the properties of the circle, is that any line that is drawn tangent to the surface will be perpendicular to the radius going from the center to the point of tangency. That's a property of a circle. You can look it up, see how they prove that property of a circle, but it is the property of a circle. So now I know I have 2 right angle triangles there. Now, what I want to get at, I want to know what this height is here. This is our hidden amount. And now I have two right triangles. This right triangle here has a side length that is the radius, 3959, plus how high we are above the earth. So I need to know how high we are, and as you'll see here, I've decided to use 10-foot observation height. So I'm going to put 10 feet there. And this here is also a radius. You'll see all of this green one's a radius, this red one's a radius, and this other green one's a radius. So this red one in here is also 3959. And this green one is 3959. And the whole thing is 3959 plus the amount that we have hidden. So what I want to do is figure out what these two smaller angles are in here, because I have all kinds of measurements, I just don't have the angles. Now fortunately this isn't a right angle triangle, and I know two sides of the right angle triangle. I know what this whole side is and this side is, so I can find this angle. I'm going to call that angle A1, angle 1. Okay, and we're going to solve for angle 1 over here. So since we're in the right angle triangle and I'm trying to find this angle in here, the sides that are around this angle are adjacent and hypotenuse, which is cosine again. So we're going to calculate the cos of angle 1. And I know that the cos of angle 1 equals the adjacent divided by the hypotenuse. So the adjacent side is 3959. And the hypotenuse is the long one, which is 3959 plus that 10 feet. Now that's going to be 3959 and 10 over 5,280. That's the fraction of a mile that 10 feet is. There are 5,280 feet, in a mile. So, and we have 10 of those. So we have to make sure that we put this in miles. And that's what I've done there. Now, in order to solve for an angle, we have to use the inverse cosine function. On most calculators, it looks like cos to the negative 1. And then we're going to do the inverse cosine of 3959 over 3959. Whoops. Little boo-boo there. 3959 and 10 over 5280. And that will give us what that angle is. So now let's pull up that calculator again. And I want to do the inverse cos. So this is how I get inverse. Inverse of cos. And in brackets, I'm going to put all of this stuff. So 3959 divided by 3959 plus that little fraction of an angle there, 10 over 5280. And that's going to give us our answer, which is really very small, 0.05604. So there it is. I just love this calculator that lets me just click over here and paste in my answer. Okay, so there's our A. Now, in order to figure out what this other thing in here is, because I need to know that angle too, we're going to call that angle A2. I know that A1 and A2 add up to theta, so in order to find A2, I'm just going to take what we found for theta and subtract what we found for A1. And that's what it's going to say under this little step thing here. To find angle A2, we need to subtract A1 from theta. So if I write that down mathematically, I'm going to say A2 equals theta minus A1. Now if we stick in the numbers, that would be theta. Whoop, where did that go? There it is. Come on. Theta, subtract this one. So you just need to subtract those two numbers. Now I'm going to pull up my calculator. Luckily it still has those numbers stored in it, stored them over here. So I'm going to take theta, let's clear this, and subtract this one. And we get 0.0370. I'm not even going to bother reading them all out. There's our number. And it's in degrees. It's nice to even put a little degree up there for me. Okay, so now that I know what this is, I'm well on my way to figuring out what this thing over here is, because it's also in a right triangle. So if I have an angle and a side in a right triangle, I can find the last side in that right triangle. And we're going to use cos again because we're doing this angle, and so I know what the adjacent side is. This time I'm finding the hypotenuse. It was the opposite in some of the other calculations that we did in previous videos, but this time we're trying to find the hypotenuse. I want to find this long side that is made up of the amount hidden plus this little bit here. So to find the long side of the triangle, aka the hypotenuse, we will use the cosine ratio with A2. So here's what we're going to do. I know that the cos of A2 is going to be adjacent over hypotenuse. So the adjacent side was just the radius of the Earth, 3959. And the hypotenuse is what we're trying to find, but the hypotenuse is made up of 3959 plus the little piece that I'm most interested in, which is h. Okay. Now we are going to go about solving for that h. We know what this A2 is. A2, I'm just going to write 0.03 down. I will use all the digits, but this side is being divided by this expression. So in order to get rid of this expression on the bottom, I'm going to multiply both sides by that expression. So over here we get 3959 plus h. And that's going to equal just plain 3959. Now this cos of 0.03, I want to get rid of it. I'm going to divide both sides because these two things are being multiplied. So to get rid of this, I divide both sides and I get 3959 plus h is going to equal 3959 divided by the cos of 0.03. Now I'm going to figure this out in the calculator. Luckily, all of these numbers are still stored in the calculator. So this 0.03 is right here. So I can just type in 3959 divided by the cosine of this number. And that's the one that I wanted there. So my result is 3959.00057. So it's not a whole lot bigger than the actual radius of the Earth. And that's what we get. Now we're not quite done because this is, first of all, it's in miles, and it still has this 3959 on it. I'm only interested in what the h is, so I need to subtract 3959 off of both sides, which is pretty easy because it's just going to be the decimal part of this one. So 0.00057 approximately. Now since this is in miles, to change it to, and I'm going to change it to feet, I need to multiply by the number feet in a mile, which is 5280. So I'm just going to take that answer that I had here and times it by 5280. And we'll get our grand total in feet. Oh, shoot. I forgot to subtract off the 3959. That would be monumental. Okay, I'm going to go back to this. Let's clear that. Let's go back to this. And, whoop, wrong one. Clear that. Insert result. I'm going to subtract off the 3959. So I just have the decimal. Now I'm going to times it by 5280. And now we get something that makes more sense. 3.018. And that is in feet. So 3 feet of obstruction is what we would get if we were 10 feet off the ground. Okay, that took a long time. I was going to talk a little bit about how you could do this a little bit quicker with the 8 inches per mile squared, but I think maybe I will think about doing another video for that since this has taken so long. I do want to take a look at the Microsoft Excel here. The easiest way, if you wanted to do this again, if you wanted to change how high you were above the surface or how far you are away from a target, again, you would have to go through this for almost 5-step processes because you have to change it into feet down here. So you'd have to go through all of these steps again, changing this number here, this 6 right in here for the area along the curve, and changing this 10 here for how many feet high you are in the air. And you would have to go through all of these steps. There's no real shortcut. There's a little bit of a shortcut if you want to use the 8 inches per mile square, but even it's a little bit more complicated than just, I can't just give you a formula, plug in those 2 numbers, and it spits it out. That's why the earth curve calculators online are like a whole calculator, because they're doing all of these steps for you. I put it together in a spreadsheet so that we could play with it a little bit more. So I have all these calculations in a spreadsheet, and you can see here the spreadsheet uses radians. It's easier to use radians. It really is actually easier in the calculations to use radians. But I converted them to degrees so that you could see that they're actually the same. So these things are just a conversion. If you look up here, to convert radians to degrees, you multiply by 180 divided by pi. And so you can see that those are the same numbers that we had before. Okay, if you want to play with this a little bit, I'm going to put in something here that let's say we're 20 feet above. What does that do to our observation height? Well, it makes it so that our amount hidden is now less than a foot, 2 inches to be exact. If I change it to 30, now 30 is going to do something weird on my calculator. What it does is it changes this to negative, which means that now nothing is hidden by the horizon. These things are meaningless once this turns into a negative angle. And they're just going to start giving you gobbledygook answers. So once you get an observation height of 30, you should be able to see 6 miles, no problem, no obstruction whatsoever. And probably something a little bit closer to there. Let's see if 25 kicks that into negative. Yeah, even 25 gives that a negative. So at 25, you should be able to see 6 miles. Okay, we're going to leave that observation height at 25, and I'm going to put something in here, 32 miles. Something that I'm familiar with is the distance across Lake Ontario, if you're looking at Toronto from Niagara-on-the-Lake, which is a splendid view that I've seen before. So if you're 25 feet above ground, which would make sense if you're back from the shore a little bit up on a bank, 25 feet is not really much when you're talking about that. You would expect to see about 446 feet of the skyline obstructed in Toronto from that distance. Now, keep in mind that none of this at all takes refraction into consideration, and refraction does bend things, so I would expect to see to have a little bit less than 446 feet hidden on any given day, and on some days maybe even more, because the atmosphere can do all kinds of weird things. I know most of the flat earth people make fun of the mirage effect, but I've actually seen this kind of thing where I see stuff that I don't normally see. For instance, coming home one night, I got to the top of a hill, and in the distance I could see all the flashing lights of some wind turbines that are near my house, and I was still about 15 miles away from where they were. And I know I don't usually see that, and I haven't seen it since. You don't usually see those flashing lights there. But there they were, and it was actually kind of shocking to suddenly see all of them spread out there, and I'm going, are those the turbines that are near my house? Because I've never seen that before. And to be honest, I haven't seen it since. It happens. where refraction can play a big part. Anyway, I think I'm going to leave that right now and catch you later.